Hello, I'm Arthur. Welcome to my lab. For one of the printers that I'm planning on building, I've decided to use 24-volt power supply to power the bed. But I don't want to use the same 24-volt power supply to power the controller board or the hot end. So I found on eBay this step-down converter that takes 24 volt, or actually a range of voltage on the input, and it will output a range of voltage including 12 volt. So you can just use this multi-turn potentiometer to adjust the output voltage. And so I can hook up my 24 volt power supply on the input and set the potentiometer to output 12 volt for the rest of my system. And I wanted to test this circuit, so I decided to get this digital electronic load that will sync whatever current you set on it from your source of voltage. A lot of times these loads are being used to test batteries, rechargeable batteries. You can test their capacity or their discharge rate, but you can also use these for other purposes. So let's take a look at this load. It requires 12 volt on the input, and you need to supply at least 500 milliamps, I believe. This is 12 volt up to 2 amps, so we're good here. It powers on, and it actually remembers your last setting. I was playing with this device, and I set it last to 11.5 volts and 4 amps load on the input. I've attached a thermocouple to monitor the temperature of the heatsink, and there's a beefy FET transistor that acts as the current sink. So it can heat up, and I wanted to see how hot does it get. You might hear the noise of the fan. Yeah, even with this device being passive and not enabled, it still makes a little bit of noise, and the air blowing through the heatsink is actually that's a pretty strong stream of air. So this heatsink doesn't really get very hot. So let's hook up my power supply. I have it set to supply 24 volts. And yeah, that's a big spark. That's because of these capacitors. Yeah, they hit the supply pretty strong when you first plug it in. It's probably much better to use the power switch on the power supply. But anyway, so right now 24 volt is coming into this DC to DC converter. 12 volt is coming out, and once I hit this run button, this DC load will start putting 4 amps load on the output. So and my voltage limit is set to 11.5 volt. So if the output voltage of this DC converter drops below 11.5, then the load will shut off and remove the load off of the converter. So we should see 12 volts here on the readout for the voltage. So let's run this thing. See, works like magic. This DC to DC converter converts 24 volt on the input, and you'll have to trust me on this one. It is 24 volts. And my power supply says that it's supplying 1.95 amps. So almost 2 amps coming in, and 4 amps of a load, which that would mean that this converter is more than 100% efficient. I think that one of the two displays isn't actually right. I'm guessing either my power supply is supplying a little bit more than 2 amps, or this isn't full 4 amps. I might plug in actually a multimeter and see how much current I have coming in. And as we can see, the temperature is rising. It's at 42 degrees Celsius right now, 43. The heatsink doesn't really feel hot. this area right here, my thermocouple is almost touching the transistor, and this part of the heatsink isn't really hot at all, and the air flowing out of the heatsink isn't hot neither. So this is nowhere near almost 50 degrees Celsius here. But I guess close to the transistor, things are much hotter. So the temperature is still rising, and we're still getting 4 amp load on this thing. (51 degrees). And actually, yeah, let me prepare my multimeter and get it ready to measure the amps. I'll measure the amps on the input. See if we really have 1.94 amps coming in, which is what my power supply is reading right now. Or actually, let's first measure current voltage, which I've calibrated that power supply to display correct voltage, but oh, there we go. So this is what I was waiting for, actually. OTP, over temperature protection. So the load, the heat on the heatsink hit, I believe it was 55 degrees. I wasn't actually looking at this right now because I was plugging in the probes here, but from the previous tests I know that it was around 55 degrees that OTP kicks in. So then the load from the converter was removed, and now the temperature is dropping because this device is not active. And you push the run button again to cancel the error condition, and now if I push the run button again, it'll start running again. So yeah, my voltmeter is plugged in and it reads 24.23 volts. So I have 24 volts coming in, and now let's switch to amp mode and measure the current coming in. And right now it's reading 0 amps because the load is turned off. Let me actually get this meter here in the field of view. Alright. So 0 amps, and we turn on the load, and 1.96 amps, and my power supply reads 1.97. So actually, yeah, it looks like this part is correct. So let's see what we have on the output. Looks like that reading is off. One thing that I don't like about this DC to DC converter is that these screw-in terminals are really tiny. This thing, I don't recall what the maximum current on it is. I'll try to look it up real quick. But I think it can handle up to like 20 amps. And if that's the case, then I think these terminals should be really much bigger. So I'm not too crazy about these small terminals. And actually, same for this load, but at least this one looks a little bit bigger. Looks like these terminals can handle a little bit bigger current, but still, I think, less than what it should be. So I would really prefer nice bigger screw terminals. And I was actually thinking about replacing these, but there isn't really all that much space available. Okay, so this DC to DC converter converts 4.5 to 30 volt on the input to 0.8 to 28 volt on the output. This is a step down converter, and it can handle a maximum of 12 amp. So yeah, 12 amp I could run through this thing, and it should be fine handling that. Alright, voltage applied to the input, and just making sure that I have my wires right. We don't want to run it through wrong terminals. Okay, looks good. Let's power it on. So it should be 4 amps, and it's beeping at me because the voltage, because of the amp meter being plugged in, the voltage drop is more than my limit. So let me change the minimum voltage drop, or actually let's adjust the output of my converter to be 12 volts. So to do that, I need to turn on the load and observe the readout on the voltmeter here. See, it almost hit that 12 volt. Is this a right screw? No, that's a Phillips. It's kind of tricky doing that with one hand. Okay, here we go. I went past the cutoff voltage, and we're good. So 37 to 38 degrees. Yeah, so my meter reads now 3.62, 3.61 amps. So that's the actual current flowing to the load. It's not 4 amps as the load claims. So I'm not really loading this power supply with 4 amps. I'm loading it with 3.6 amps. So something to keep in mind when you test this stuff. Looks like you need to plug in a meter and verify the output. I wonder if there's a way to adjust the firmware, adjust the readouts. I didn't really see any trim pots to correct the readout. So I'm guessing not, unless you can lay your hands on the original firmware for the microcontroller that controls this, which this device coming from China probably won't be very likely to happen unless somebody develops a custom firmware and publishes it online. And my thermal cutoff will probably kick in just a moment as it reaches 55 degrees here. So yeah, that's the load. That's what happens at 4 amps, and once the cutoff kicks in, I'll let that heatsink cool down a little bit, and we'll increase the load to 5 amps. 54, yeah, there we go. It hit 55 or just before it, over temperature protection. So, all right. So we're at 4 amps. Let's increase that to 5. And look what's happening. This thing is advertised to have maximum load capacity of 9.99 amps. So why is it not going past 72? Well, I was wondering that for a moment. And then I realized that besides having a maximum of 9.99 amps, it also has a limit of 60 watts. And because I'm supplying here 12 volts, or actually probably at this point a little bit higher, because I had to increase this output voltage to compensate for my meter being in the circuit. So I'm probably hitting this thing with a little bit more than 12 volt. And 12 volt multiplied by 4.72 is close to 60 watts. So the maximum that you can get this thing to at 12 volt input voltage will be around 4.72 amps. And now that it cooled down, let's turn it on and see what the actual amperage is. It's 4.3. So this thing is about 400 milliamps off on the readout. So really it should be loading at this converter with 4.72 amps, but we're only putting 4.28 amps on this converter, which it's still doing fine. And I have 2.41 amps on the input right now according to my power supply, and 4.27 on the output, which that's what I would expect. 2.41 at 24 volts multiplied by 2 will be 2.8 or 4.8 amps on the output, minus the loss because the conversion, of course, is not 100% efficient. That turns out to be 4.27. I'm not going to do the math right now in my head, but usually you can expect around 90% efficiency out of these things, somewhere between 85 to maybe 95 for the best out there. And this certainly is not one of the best converters, although it is doing a very nice job. So to confirm my theory that this cutoff or the maximum load is limited by the microcontroller based on the voltage coming in, let's plug in or let's connect a different source of voltage. Let's hook it up to my power supply and see what happens when I supply 5 volts on the input. Let's start there and then go up and see what happens. While I was recording this second part of the video, my phone stopped recording. I think it just ran out of memory to store the video, so I've deleted some videos, and hopefully I'll be able to finish this video. So we started looking at why this load would top off at a certain level at 5.2 amps, even though the advertised maximum is 9.99 amps. And so my conclusion was that this happened because my input voltage was 12 volts, and because the maximum capacity that this load can handle is 60 watts, 12 volts multiplied by whatever that number was that it was topping out of was 60 watts. So it wouldn't go higher. So then I reduced my input voltage to around 6 volts, and I wanted to increase my load capacity to something higher. At 6 volts, I should be able to go to 10 amps, because that would be again 60 watts. So the 6 volt is the maximum input voltage at which you can use the full capacity, full 10 amps load of this unit. So now that we're at 6 volts, let's see if we can go up to, yep, that's actually switching my cutoff voltage. So let's see if we can go to 10 amps. Nope, still not going. And the reason is that my cutoff voltage is set to 11.5 volts. So this unit takes both the input voltage and the cutoff voltage into consideration when calculating what the allowable maximum current might be. So let's switch this to a lesser cutoff current, and 6 volts probably being the maximum at which I should be able to reach my full capacity. So now that we're at the cutoff voltage of 5.5 volts, let's see if I can go all the way up to 9.9 volts. I may need to, let's see, reduce the input voltage. Even though it's under 6 volts, this thing isn't perfect. It may be measuring differently internally. Yep. So by lowering my input voltage, I was able to reach the maximum capacity. So now if I were to increase my cutoff voltage, I'm expecting this to start dropping because it will know that I'm allowing more voltage to come in. So let's see. Yep, there we go. As I increase my cutoff voltage, the maximum current is lowering. And the same will happen if I increase the input voltage. This maximum current will lower. So let's see. See? I'm increasing my input voltage and my maximum current is dropping. So at 12 volts, the maximum that you can put on this load, oh, actually I went a little too far. Let's see, 12.4. Yeah, close enough. Right here. So the maximum load would be 4.95 amps. That multiplied by 12 is 60 watts. So let's set this back to 11.5. So if you plan on measuring something under 6 volts, you're golden. You can go up to almost 10 amps. For my application, this is a bit limiting because my hot end and the printer controller and all the stepper motors combined comes out to be, I think, somewhere around 7 amps, I want to say. Don't quote me on this, but I think that's what it was when I last tested that. So I wouldn't really be able to measure full capacity of my DC to DC converter with this unit. But still, I'm very pleased with how this unit performs and what it can do, and I'm sure I will use it many times in my lab. And meanwhile, I will probably just hook up my printer as the load to the output of my DC to DC converter to see how it behaves under the load of an actual printer. I just won't turn on the bed because that would overload it. And I just tried turning on this load and see what happens, but the overcurrent protection kicked in, or actually under voltage kicked in, because my power supply is set to limit the current to only 400 milliamps. So let's increase the maximum current that my power supply would output. And yeah, now we're at 4.58 amps coming out of the power supply. And yeah, my limit was 4.95. And again, this readout is a little bit off, about 500 milliamps. So yeah, that adds up. My power supply reads 4.56 plus 500 milliamps. That's 5.06. 4.95. Yeah, that's close enough. And as you can see, the temperature is increasing again. And yeah, I can touch and hold my finger on the heatsink. It's not that hot. The air flowing out of the heatsink isn't hot at all. It's actually chilly, but I probably don't want to touch this transistor. Might be a little bit too hot. Let's do a quick touch. Yeah, this is on the hotter side. Still, I can touch it. Not bad, but yeah, getting there. And this nice and chilly. So, well, now it started, yeah, getting a little hot. So I think that thermal cutoff is maybe a little bit overzealous. Maybe you could still squeeze a little bit more out of this unit. I may end up just replacing this heatsink with a bigger one to better dissipate the heat and allow this unit to work for a little bit longer before the thermal cutoff kicks in. So that's it for today. See you guys later. Actually, a couple more things that I forgot to mention. I was talking about the heat dissipation of this heatsink and how it reached the temperatures of around 50-55 degrees, and the fact that it will probably help to put a bigger heatsink on this unit, which is actually something that I read somewhere online that someone did that. They used heatsink from an old CPU, and that solved the problem of overheating. But I didn't talk about the heat of this DC to DC converter. Well, as much as I could load it up to almost 5 amps, this unit didn't even break any sweat. It was cool to the touch, and so it can handle load of about 5 amps with no problem. So that's one thing. And the other is, while I was reading about the electronic loads, I came across a video of Dave Jones from EEV blog, where he talks about an electronic load that he built from his scrap parts, just some parts that he had floating around. And a couple of days later, I came across this guy, which I forgot that I even had. It's 10 watt, 0.22 ohm power resistor. So that's really nice, 10 watt. And immediately I thought of that video that I saw of building a DC load just for fun from scratch parts. So I have this. I also have a MOSFET that can handle a pretty beefy current. It can go up to 60 amps actually. So I'll be using that. And I was waiting for 2 more pieces of that puzzle, which also came in today. One is this voltmeter. I'll have to play with this and see how it performs. But you see a lot of cheap voltmeters similar to this on eBay that only have 2 wires. And basically the reason why they have 2 wires is because whatever voltage you apply to this unit as supply voltage is also what it measures. But that, of course, means that there's a minimum input voltage that this unit can handle, or those units can handle, which is the minimum supply voltage for the unit to operate. This unit has a separate measurement input, separate wire, so you supply whatever voltage this unit needs to measure the voltage, and also supply your input voltage on a separate input, which means that it can go down to 0 volts, which is what I needed. So it costs a little bit more. It took a little while to find it, but it looks very promising. I'll be playing with this soon. And the other piece of the puzzle is something I always wanted to play with. It's this multi-turn potentiometer that has very nice dial, has a little window that shows you the hundreds, and then tens and units are on this rotating knob. And you can lock it in place so it won't turn, or you can unlock it and then adjust the setting. So this is how it looks like. Just your usual potentiometer, 3 terminals, just like always, except it's a multi-turn unit, and it comes with this very nice knob. So I'll be using this as means of setting my current on the electronic load that I'll be building. All right, I hope that this time I'm not forgetting anything, and that's a wrap for today.